In this video, we'll see how to build an Astable multivibrator using the IC555. The IC555 without external inputs works like a bistable multivibrator. The output can be controlled by using the pins 2 and 6. We want to convert this into an Astable multivibrator, meaning that it will oscillate between two unstable states. So, we want the output of the timer to oscillate between 0 and 1. This means that the voltage at pin 6 needs to be periodically greater than 2/3 VCC for a fixed duration of time, to get a low output. Similarly, pin 2 needs to be periodically below 1/3 VCC for a fixed duration of time. We do this by connecting an external RC circuit, consisting of capacitor C and resistors RA and RB. The charging and discharging of the capacitor will dictate the voltage at pin 2 and pin 6, which we tie together. Assume that initially the capacitor C is uncharged and the output of the flip-flop Q is high. Hence, the transistor will be off, and the capacitor will charge via RA and RB towards VCC. The capacitor will follow an exponential relationship as it is part of a first-order RC circuit. The capacitor voltage is fed to the trigger and threshold pins. Hence, when VC goes above 2/3 VCC, the output of comparator C1 goes high, thus resetting the flip-flop. The output of the timer also becomes low. Q bar becomes high and the transistor T turns on. Hence, the capacitor finds a path to discharge through RB via T and thus, VC starts decreasing. When VC goes below 1/3 VCC, the output of the comparator C2 becomes high and the flip-flop is set again. The output of the timer becomes high again. At this point, the transistor turns off again and the capacitor starts charging via RA and RB. This cycle repeats continuously and we get the following waveforms. Let's find out TH, which is for how long the output is high, and TL, for how long the output is low. Assume that T equal to 0 is the instant at which the capacitor starts charging from 1/3 VCC towards VCC. As the capacitor charges via both RA and RB, the time constant will be RA plus RB into C. We can write VC as VC will be high until it reaches 2/3 VCC. Hence, substituting VC of T as 2/3 VCC at T equal to TH, we get the following equation. Solving this, we get TH as RA plus RB into C into ln 2, which is 0.69 RA plus RB into C. During TL, the capacitor will try to discharge from 2/3 VCC to 0. As it discharges via RB, RBC is the time constant. Hence, assuming T equals 0 as the beginning of the discharge of C, we can write the equation for VC of T as 2/3 VCC into e raised to minus T by RBC. Discharging will end when VC is 1/3 VCC. Hence, substituting VC of T as 1/3 VCC and T equals to TL, we get TL as RBC ln 2, or 0.69 RBC. The total time period is TH plus TL, which is 0.69 into RA plus 2 RB into C. That means that 1/T, which is 1.443 by RA, plus 2 RB into C is the frequency. The duty cycle can be calculated as TH/T into 100. For this circuit, the duty cycle will always be greater than 50%. Usually we want to achieve a duty cycle of 50%. If you look at the equation for duty cycle, it seems that if RA becomes 0, the duty cycle will be 50%. However, making RA 0 will result in the collector of the BJT being shorted to VCC. That implies that the transistor can never go into saturation. Another thing we can try is making RB as much greater than RA, which allows the duty cycle to approach close to 50%. Alternatively, we can use a diode in parallel to RB. The diode will short out RB during the charging cycle. Hence, while charging the capacitor only charges through RA, and while discharging, the capacitor only discharges through RB. If we choose RA equals RB, we get a duty cycle of 50%. Since we're using the RC network to control the timings and not the control pin, it is grounded by a 10 nanofarad capacitor to provide immunity from noise. That's all for this video. If you have any doubts, feel free to ask in the comments section below. Don't forget to like, share and subscribe.